Good morning, chemistry students. Here are your Chapter 13 notes for Day 3. We'll be starting in your outline at 13.2 electron arrangement in atoms and finishing up the orbital notation section. So again, all of the chemistry that happens in atoms and in forming chemical bonds and chemical reaction is because of what the electrons are doing. So because of that, it's super important that we know where the electrons actually are in these atoms. So remember with the quantum mechanical model, okay, we've talked about the fact that we have the energy level, and then within that energy level we have the sub-level, and the sub-levels can be S, P, D, or F. And remember, they go in order of energy from S, P, D, F, S being the lowest, F being the highest energy. Okay, so that's the sub-level. The sub-levels have orbitals within them. How many orbitals depends on the sub-level. S sub-levels only have one orbital, one S orbital. P sub-levels have a total of 3 orbitals. D sub-levels have a total of 5 orbitals, and F sublevels have a total of 7 orbitals. Remember, each orbital can only hold 2 electrons. Okay, so again, all of the chemistry that happens is because of where the electrons are. So knowing where the electrons are will allow you to predict what kinds of reactions are going to take place. Because when we finish up this unit, we're going to talk about ionic compounds and covalent compounds, and ionic bonds and covalent bonds. Okay, and being able to predict what kind of bond happens will be dependent upon knowing where the electrons are in the atoms. So 13.2 electron arrangement in atoms. We're going to start by talking about electron configurations. The definition of electron configurations. Okay, electron configurations is defined as the ways in which electrons are arranged in various orbitals around the nuclei of atoms. So again, basically we're just talking where are these electrons in these energy levels, in these energy sublevels, and in these orbitals around the nuclei of these atoms. In atoms, the electrons and the nucleus interact to make the most stable arrangement possible. Okay, so always atoms are looking to be as stable as possible in terms of energy. So they're always going to default into that most stable configuration. So there are a total of 3 rules to follow when we're talking about electron configurations and figuring them out. These 3 rules to follow, okay, tell us how to find the electron configurations of atoms. So using these 3 rules, by the time we're done with this, you should be able to write the electron configuration of any atom on the periodic table. Now, today it is definitely going to be necessary for you to have a periodic table to look at. So hopefully you have a periodic table printed out and kind of sitting next to you as we do our notes today. So the first rule is the off-bow principle. The off-bow principle states that electrons occupy the orbitals of lowest energy first. Now, on your ChemQuest, there was sort of a big, long list so that you could remember or learn the order that these electrons occupy these orbitals. I'm not going to have you memorize that list. I'm going to teach you how to use your periodic table to know the order of all of the orbitals in terms of energy, because your periodic table already has it in order. So instead of memorizing a list of orbitals, you'll learn to use your periodic table. So before we get to that, the orbitals of any sublevel of a principal energy level are always of equal energy. So all that's really saying is within that p sublevel where there are those three different p orbitals, all three of those p orbitals have exactly the same amount of energy. Within the d sublevel where there are the 5 different d orbitals, all of those 5 d orbitals have exactly the same amount of energy. And within the f sublevel where there are those 7 different f orbitals, all 7 of those have equal amount of energy. Okay, so we'll kind of write that in our notes here. So the 3 p orbitals all have equal energy. The 5d orbitals all have equal energy, right? Those are ditto marks, which is a way to save you writing some things in your notes, because it just means whatever's above it. Okay, and finally, the 7f orbitals all have equal energy. Okay, so that's all we're saying. There's no difference in energy, so it really doesn't matter which one of the p orbitals I put an electron into, they all have equal energy. Same thing is true for the d's and the f's. Within a principal energy level, right, and that's kind of like the main energy level, the s sublevel is always the lowest energy. Sublevel. Okay, and going from low to high energy within that principal energy level, the order is always the same. The order is always S, then the P, then the D, and then the F. Okay, so what that really is saying is we will never have electrons into the P sublevel before the S sublevel of that energy level is full. We will never have electrons in the D sublevel before the S and the P sublevels of that energy level are full. Okay? So we'll always, when we start out in a new energy level, we'll always put electrons first into the s orbitals, and then the p's, and then the d's, and then the f's. It's always in that order. So how do we use our periodic table to know this order? Okay, it's not something that you have to memorize. So the first thing you have to know is that technically helium here, we could put here. It fits just as well here. And for our purposes today, we want to kind of put helium there. Okay, oops. All right, got to put that picture back in. Sorry about that. There we go. All right, so I just don't want to put it in red. So I'm going to put helium here because it fits just as well there. And for our purposes, the way we're going to talk about things today, we really want to have helium sitting over here. Okay? So, remember, okay, or a couple things here. First off, these period numbers here, these are our energy levels. Okay? So these are our energy levels. And your periodic table should have those numbers on them as well. So all that's saying here is in the first row, we're in the first energy level. In the second row, we're in the second. In the third row, we're in the third. In this fourth row, we're in the fourth energy level, and so forth. Okay? So that's all that I'm saying here is those numbers there correspond to our energy levels. All right? So next, remember, level or layer of this is the sublevels. So for the sublevels, remember the S sublevel only has one orbital that can hold 2 electrons. That's right here. Right? Remember, not only are my number of protons changing here, but so are my number of electrons. So lithium has 3 protons and 3 electrons, and beryllium has 4 protons and 4 electrons, right? So we've changed the number. So we're going to talk about atomic numbers right now, but we're going to focus on that atomic number telling us the number of electrons. Okay, yes, it also does tell us the number of protons, but again, all the chemistry is with the electrons. So right now we're really focusing on it telling us the number of electrons, right? And for lithium and beryllium, the difference between them is 1 electron. So these 2 tall columns on the left-hand side of the periodic table, these are called the S block. And we call them the S block because in the S block, we're putting electrons into S orbitals and the S sublevel. Now remember, the P sublevel has a total of 3 different orbitals, each holding 2 electrons, so that's 6. Notice over here I have 1, 2, 3, 4, 5, 6. That's not a quinky dink. This is my P block. Over here, I'm putting electrons into my P orbitals. All right? My D block, right? We want to talk about my D sublevel next with my 5 orbitals being able to hold a total of 10 electrons. Again, notice across here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? This is my D block. What that means is I'm putting electrons here into my D sublevel and into D orbitals. Now, this periodic table, these 2, in my opinion, should be right here and right here. Okay, so we're going to kind of ignore these 2 here. Now, remember, I still need to talk about my F block, right? And in my F sublevel, I have a total of 7 orbitals holding 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, you guys, that's not a quinky dink. This is called my F block. What that means is, in these two rows that are pulled out and underneath the main body of the periodic table, we're putting electrons into the F sublevel. We're putting electrons into those 7 F orbitals. So remember I told you that your periodic table was going to tell you a whole lot more than just atomic number, element symbol, element name, and atomic weight. Right? As you start to look at it now, you're going to start to see some information about that quantum mechanical model that Schrodinger has developed and that we still accept today as our model of the atom. Now, when we're filling our S block, okay, and when we're putting electrons in here, it's always equal to our period number. Because remember, our period number over here is our energy level. So for hydrogen and helium, I'm putting electrons into the 1s orbital. For lithium and beryllium, I'm putting electrons into the 2s orbital, and so forth. So for example, cesium and barium, those electrons are going into what orbital? The 6s orbitals, because again, I'm in the 6th row, and s is equal to the period I'm in. That's also true for my p block. So I'm just going to kind of add those numbers over here as well. Okay, so when I'm talking about aluminum to argon, I'm going to be putting electrons into the 3p orbitals because I'm in the 3rd row and because I'm in that p block section. If I'm talking about thallium to radon, I'm going to be putting electrons into the 6p orbitals. Okay, so for p's, also equal to our period number. Now, for D and F, it changes a little bit. The D block is 1 behind, so it's going to be equal to our period minus 1. So when I talk about scandium to zinc, right, those are in the 4th period, but the D block is 1 behind, so those are not 4 Ds, those are 3 Ds. Okay, so these are my 3D orbitals. So if I take a look at lanthanum to mercury, right, I'm in the 6th period, but I'm 1 behind, so these are actually the 5D. Right, so uridium to cadmium will be my 4Ds, and actinium to whatever this is that I'm written on, number 112, those are going to be my 6Ds because they're always 1 behind whatever period I'm in. When I get to the F block, the F block is 2 behind, so it's my period minus 2. Now remember, right, technically these are in the 6th period and the 7th period, right, because they came out of the periodic table where lanthanum and actinium are. So, again, these are Fs, but they're 2 behind the 6, so these are 4F, and these are 5. Let me change my color there so it'll show up. These are my 5Fs. So, remember on our ChemQuest, it was a big, long list of all of the orbitals in order of energy. And I'm saying you don't need to memorize that. I'm saying we're going to use our periodic table to give us that information. So, let's choose a good color here. Pretty much all these colors are on the periodic table. Let's try kind of this really bright pink color. All right. So, in order of energy, from lowest energy, I'm always going to start up here at the top left-hand corner. I'm going to read my periodic table like it's a newspaper, working towards this bottom right corner, right? So, The first orbitals in terms of energy that I come to are 1s. Let me change that. I want to make this the color. There we go. All right. Here are my 1s. And notice I'm out of electrons. Right? Remember, the first energy level is kind of different because it can only hold 2 electrons total, because it only has, the first energy level can only have one sublevel, which will be the s that only holds 2. After 1s, I come to 2s. Next, I have my 2p's. Next, I come to my 3s. Next, I come to my 3p's. Next, I come to my 4s. And then I come to my 3Ds. Now, what does that mean? That means that a 4s orbitals are actually lower in energy than the 3Ds are in terms of energy. Again, I don't have to memorize that or remember that every time because my periodic table tells me that. My periodic table already is putting electrons into the lowest energy orbitals first because of the off-ball principle. So after my 3Ds, next I come back to my 4Ps, because remember Ps are equal to the period I'm in. Next I come to my 5s, then my 4Ds, because they're one behind, my 5Ps, 6s. In terms of number, notice next number-wise, there's a skip in my numbers. So next I come to my, after my 6s are my 4f's, then my 5d's, then my 6p's. Next I come to my 7s, then my 5f, and then my 6d's, and then my 7p's. So what I'm saying with this is you don't have to memorize some list of orbitals. You might have a college professor that tells you have to memorize that. And I hope at that point you remember back to Mrs. Krumschreider saying, no, I don't have to memorize that. I have a periodic table. No chemist ever functions without a periodic table at their fingertips. And by using my periodic table and understanding my S block, my P block, my D block, and my F block, I don't have to memorize some list of orbitals in terms of energy. My periodic table already tells me. Okay? So that's what we're going to use as we start to look at these electron configurations. So that was, again, our off-bow principle. Our second rule that we have to follow when we're putting electrons in atoms is the Pauli exclusion principle, which says that an atomic orbital may describe at most 2 electrons. Now again, you've already seen this on that ChemQuest we did, right? So remember I told you that we're doing ChemQuest as like a preview of what we're going to talk about in notes to sort of start to get you ready to learn this new information, okay? So what we're saying here is an atomic orbital, right? So an s orbital can only hold 2 electrons. Any one of those p orbitals can only hold 2 electrons. Now remember, that's why there are 2 columns here, because S block can only hold 2 electrons. Over here for the P block, that's why there are 6 columns here, because there are 3 P orbitals, each holding 2 electrons, right? And for the D block, there are 5 orbitals, each holding 2 electrons, which gives us 10. And the same thing is true for the F block. There are 7 orbitals, each holding 2, which gives us 14 electrons. Okay, so again, Pauli exclusion principle says an atomic orbital may describe at most 2 electrons. To occupy the same orbital, two electrons must have opposite spins. Remember, that was that final quantum number we looked at, that ms, and it was a plus 1/2 and a minus 1/2. Now, the electron spins may be paired. So you can have two electrons, and if you do, those spins are going to be paired. Spin is a quantum mechanical property of the electron and may be thought of as clockwise, oops, not cloudwise, clockwise, and counterclockwise. And again, remember, our spin is represented, I don't know if you can hear the dog itching herself or not, represented with vertical arrows. Right? Up meant clockwise, and a down arrow meant counterclockwise. And again, these arrows, right, represent. All right, just to make sure, I'm pretty sure it was still going when I was talking about Hund's rule, but we'll go over this again. Electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. For P, D, and F sublevel, that means that you're going to put one electron into each orbital before you double up. Okay, so again, that P sublevel, I'm going to have one electron into each P before I start to put an electron into a second energy level, and so forth. Oh, I hope that it didn't skip more than that. I'm sorry if it did. If it did skip more than that, someone has to email me and let me know what part you missed. Okay? All right. Back to orbital notations, or this orbital filling diagram. The orbital is indicated with a box or a line and is always labeled. And the electrons are represented by the up or down arrows. So we're going to do a bunch of examples of these. Right? I like lines, but technically you could do a box. So technically you can write a box and write one S under it. I don't like to make boxes. I like to make lines. So we're going to start first with hydrogen. And so remember, we were going to look at our periodic table and figure out how many electrons hydrogen has. It has an atomic number of 1, which tells us it has 1 electron. So here's hydrogen. I'm labeling my line. It's going to be the first main energy level because of where it is on my periodic table, right? It's in my first period. And in my first period, I can only have my S sublevel, because in the first period, I can only have one sublevel, which is my S, and my S only has 1 electron. So here's my orbital notation for hydrogen. All right, next we're going to look at helium. Helium has 2 electrons. It's still in the first main energy level. It's in period 1, so it's 1, and then it's S. And I can only have one sublevel, the S, and helium has 2 electrons, so here's my arrow up, and here's my arrow down. Next, we're going to look at lithium. Lithium has atomic number 3, so it has 3 electrons. So again, we're always going to start at our 1s, because we're always starting at this upper top quarter of our periodic table. Right, and 1s completely takes us to the end, and so now we're into our 2 because we're in the second energy level, and S because we're in our S block. And next, So we have to write that 2s next, because that's what we come to next. And then here's our electrons. Here's my first electron, my second electron. Remember, I have to completely fill this orbital of lower energy before I put an electron into the next one, right? That is that off-bound principle. So here's my third electron for lithium. We're going to skip a few and go to carbon next. Carbon has an atomic number of 6, so it has 6 electrons. Okay, so again, how do I kind of use my periodic table here? Let's see, let's try this kind of weird color, right? So I want to get to carbon that's here. So here is my 1s, so that's going to be first. Next I come to my 2s, and then I'm in my 2p. So for my lines, I'm going to have 1s. Next I came to my 2s, and again those only have one line because s orbitals or s sublevel only has one orbital. When I get to my 2p's, right, remember my p sublevel has 3 different orbitals. So now I'm ready to put my electrons in. Again, my first one and my second one go in my first energy level, my 1s. Number 3 and 4 are going to go in my 2s, because again, I have to have that completely full before I go into my next energy sublevel. So now I need 6 electrons total, so that leaves 2. Now, this is that Hund's rule that says that I'm going to put electrons into different orbitals before I start to pair them up. Okay, so I'm only going to have 1 electron in each orbital there. All right, after carbon, we're going to look at nitrogen. Nitrogen has atomic number 7. So again, when I look at my periodic table, the first energy level I have is my 1s. Next I come to my 2s, and then I come to my 2p's. Right? Nitrogen is just right next to carbon. It's still in that second p block. My 7 electrons, here's number 1, 2, 3, 4, 5, 6, 7, right? Hund's rule says I'm going to put 1 electron into each orbital before I start to double up. Next, we're going to look at oxygen. Oxygen has atomic number 8, so it has 8 electrons. So again, I have 1s first. Next, I come to my 2s. And again, it's still in the second energy level in that p block, so it'll be my p's. 8 electrons, so here's number 1, 2, 3, 4, 5, 6, 7. Right now, they're all completely full, and I have to start to double up. And just by convention, we normally go back to the first one. So there's my 8 electrons in oxygen and my orbital diagram for it. Next, we're going to look at fluorine, which has atomic number 9, so it has 9 electrons. It's still in that second p block. So again, I'm still going to start with my 1s first. Next, I come to my 2s, and then I'm going to come to my 2p. There are 3 2p's because there are 3 different p orbitals. All right, so for fluorine, 9 electrons. 1, 2, 3, 4, right? I have to fill them that way because I have to completely fill my 1s orbital before I put any electrons into my 2s orbital. I have to completely fill my 2s orbital before I put any electrons into my 2p. So that's 4. Here's number 5, 6, 7. I have to do that way because of Hund's rule. 8, 9. So there's my electron configuration for fluorine. All right, we're going to do 3 more total. So next we're going to look at neon. And neon has atomic number 10, so it has 10 electrons. It's still in that second p block, so I'm still going to start with my 1s. Next I come to my 2s, and then I come to my 2p with the 3 different orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice that neon's first energy level is completely full, and its second energy level is completely full. We're going to see that happen all the time when we're talking about our noble gases, that group 18 or 8A. And that's why they are not going to get involved in forming chemical reactions, because they're already very stable, because all of their energy levels are completely full. All right, next we're going to look at sodium. Sodium is atomic number 11. So again, we're still going to start out with 1s. Next, we're going to come to 2s. Then we have our 3 2p's. However, right, sodium has 3 electrons, and it's actually located in that s block in the third period. So next we have our 3s. Again, remember what this says is, here's my orbitals of low energy. Here are my orbitals of, high energy. Okay? So I'm always doing this in terms of energy. So putting my electrons in, 1, 2, 3, 4, 5, 6, 7, because of Hund's rule, 8, 9, 10, because the off-bound principle says I have to have this 2p completely full before I put an electron in my next higher energy level, which is my 3s. All right, so here's what I want you to do. I want you to try bismuth. So see if you can use your periodic table to do the orbital notation for bismuth. Now, I'm going to ask that you go ahead and pause your video for however long it takes you, and then kind of resume it when you're done so that you can see my solution. So please pause it now. Right? I'm just using my periodic table, kind of tracing my finger across it, right? So first I come to my 1s. Next I come to my 2s. Next is my 2p. Next comes to my 3s, so I'm at sodium and magnesium right now. So next I come to my 3p, and there are 3 of them. That takes me to argon. So now I'm on my 4s, which takes me to potassium and calcium. Now I come to my D's, and remember my D's are 1 behind. So although I'm in the 4th period, these are 3 D's. And there are 5 of them, right? Because d orbitals have 5. So there are my 5 3Ds, which takes me to zinc. So now I'm at gallium, and I'm back to my 4Ps. Oops, put that one in the wrong spot. After my 4p, right, that takes me to krypton. Now I come to my 5s. After 5s, uridium to cadmium are my 4ds. So 1, 2, 3, 4, 5. Those are my 4ds. Now I'm at indium and going to xenon, and I'm in my 5th. So these are my 3 5Ps. Okay, so I'm at xenon, right? And I'm going to bismuth, so I'm going to be there in my next row. So next I come to my 6s. That takes me to barium. Now, here's where I have to be careful, right? Because next, in terms of numbers, Remember, I get to one of those ones that's pulled out underneath, which are my F's, and they're 2 behind, so I'm in the 6th period. So these are going to be 4 F's, and there are 7 of them. So there are my 4 F's. All right, that pretty much takes me to luteum number 71. So now I'm ready to do 57 through 80, which are my D's, and I'm 1 behind, so I'm in my 6th period. So those are 5 D's, and there'll be 5 of them. So there's my 5 D's. Almost there, right? Because now I'm into bismuth, which is in my 6 P's, right? So I'm going to have 3 of them and their P's. Okay? So now I'm ready to put electrons in. Bismuth has 83 electrons. Okay, and I'm going to do them in a different color. So we'll do blue. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? I'm at 18 electrons. I'm at argon right now. 19, 20, 21, 22, 23, 24, 25, 26. Oops, sorry, I went too far there. 25, 26, 27, 28, 29, 30. So that's at zinc. I'm at atomic number 30 zinc. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, right? So 43 takes me to technetium, atomic number 43. 44, 45, 46, 47, 48 takes me to cadmium. 49, 50, 51, 52, 53, 54. Right? 54, I'm at xenon right now. Getting close. 55, 56. 57, 58, 59, 60, 61, 62, 63, right? Right now I'm at europium. 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80. So right now, number 80, I'm at mercury. 81, 82, 83. Hopefully you did that correctly. Now, the last thing we want to talk about is there is something called being half filled. And half filled looks like this. Okay, half filled means I have an orbital and I just have 1 electron in it. So how many electrons does bismuth have in a half filled orbital? 3, right? When I go over here to oxygen, how many electrons does oxygen have in a half filled orbital? 2. Fluorine has 1. Neon does not have any. Sodium has 1. Hydrogen has 1. Notice helium doesn't have any. It's in that noble gas group. Lithium has 1. Carbon has 2. And nitrogen has 3. So that means just a half-filled orbital. So that brings us to where we're going to stop for today. You don't have any homework. Have a good day. I'll talk to you tomorrow.